All right, so let's start. So the problem I want to solve is, actually I forgot what it was. It was a simple supported beam, wasn't it? And it had 2-point loads, P and P, and these were all L apart. We're going to find the shear force and bending moment. So what I suggest we do, and it's a good idea, is to find all your reactions to get started. So I'm going to slide over here and find those reactions. I'm going to go ahead and assume that I have a reaction force, I'll call it AY and AX, and over here at the roller, a reaction force, which I'll just call BY. So let's find those reactions. So I'll come over and I will sum the moments about A, and that'll help me find the reaction at BY. So looking at these two forces P and their effect around A, is that positive or negative moment? Negative, right? So the first one will be P times the moment arm of L. The second will be minus P times 2L. And then I'll have BY, which creates positive, and it'll have a moment arm of 3L. So what is BY equal to? Believe it or not, it's P. Okay? That shouldn't be a surprising result. The loads are symmetric, so you'd expect half to one side and half to the other side. I'll go ahead and do the statics, but you probably are already looking ahead and seeing that AY plus BY minus P should be in equilibrium. Of course, if I put BY in here, AY is also P. Again, I don't want to be too negative, but if you don't do your reactions right, everything else is going to go badly for you. Now, what I like to do at this point is draw like a template. So I'm going to draw some vertical lines that establish the left and right limit of my problem. I'm going to look at my loading and see if I see any discontinuities. Well, I know I've got these point loads. So what's the load from 0 to L? 0. And then it abruptly changes, right? So I think something's going to happen there and at this other point load. If I had distributed loads that started and stopped, those points would be probably interesting too. And then I'm going to come down here and I'm going to establish an x-axis and a shear axis. And I'll go ahead and say that, although this is a symbolic problem, I'm going to assume all my values on my diagram are going to be in kips, or whatever unit the problem happens to want. Okay? Now, starting from left and working to the right, because that's where my positive axis is. Remember, all my derivative relationships that we just talked about are also built that way. So just so you don't forget, I'm going to come over here and say we know that the change in shear with respect to x is W, and that, the slope of the shear diagram is equal to W. The change in shear is the integral under the load curve. So these are my two related properties that are going to help me construct my shear diagram. So let's start here. What do you think the shear at point A is? Well, we found AY is P and AY was up. A shear on the left side acting up is positive or negative? Remember the sign convention for shear? That's positive. So I know I'm going to have a positive shear value of P there. Let's go over here and look at BY. I assumed BY was up, and I got a positive result, P, so it is up. Now, what kind of shear force is up on the right-hand side? Negative. So I know I'm going to hit negative P. So I know where I'm starting, and I know where I'm ending. I just need to connect the dots. Yeah, in case you forgot, remember that if you have a blob, forces that look like this are positive. And you can see BY does not match that. So it must be negative. Okay? So, let's apply this one first. Change in shear. So the change in shear from 0 to L is the area under the load curve. What is the area under the load curve? 0. So that means there's no change in shear. So if I start at P, I have to stay at P. What's the shape of the curve in between? Well, I can imagine any number of curves that would fit those 2 points. Which one is correct? Why? Because the slope of the shear diagram is equal to the load, and the load is 0. What kind of slope is 0 slope? A horizontal line.
Can you explain that one more time?
Which part?
I don't know why. Why did you put P up?
Because I know I start with, well, AY is equal to P. And we know up on the left side is positive shear. So I start at positive P.
Okay. Oh, so you're looking from that? And
Yeah.
then move to
I'm
the
starting
right.
where I know, and I'm going to try to build it towards where I know on the other end.
Gotcha.
Now, this is just to the left of P. What happens when I go just to the right of P? What's the change in shear as I go underneath a load? It's equal to that load. And that load is positive or negative? It's acting down. Negative. So if I'm at positive P and I drop P, I'm at 0. Now I want to move from L to 2L. So what's the change in shear from L to L? It's the area of the load curve. And what's the load curve between L and 2L? 0. So there's no change. What's the shape of the curve in between? According to this, it's the value of the load. And the load is 0. 0 is a horizontal line. Now I'm just to the left here, and I go just to the right. How much is my shear change? Positive P or negative P? Negative P. What's wrong, Ms. Wiseman? You're shaking your head. You like it? Sure. That sounds very comforting. Sure. Yeah, I got it. So that would drop to minus P. Okay? So here I'm at minus P. I want to move another distance here. It says the change in shear is equal to the area of the curve. What's the area of the curve from here to here? 0. No change. Minus P plus 0 is minus P. Yes! I made it home. I found my minus P. I have found the path that connects the 2 dots from where I started to where I end. That makes me feel good. Now what's the shape of the curve here? According to this, the slope of that curve is equal to the load. The load is 0. It's horizontal. So I'll just do this so that you can see the area. There's my shear diagram. Now look how much work I did to get that. I didn't have to write 3 sets of equations and then plot them. Now we need to talk about this now. If you don't understand this, we need to do it now. Because we're just going to do it again and again and again. And we're going to apply the same ideas with the shear diagram to generate the moment diagram. So maybe while you're formulating your questions, I'll go ahead and say, well, let's consider positive x and positive moment. And moment usually has force length, so I'll say kip feet. Now, what do we know about moment?
Maybe has a question. Well, let's be going down at negative again.
Well, we know By, when we solve for it, is a force acting up. But now this is a shear diagram, not a reaction diagram. Right? So we know that a force on the right-hand side is down is positive shear. Is this a force acting down? So it must be negative. All right. Where do we know the moment? What is the moment at an external pin? 0. What is the moment at an external roller? 0. Not very exciting, but we know where we're starting and we know where we're going to end. So let's find the right path between those 2 points. Okay, to do that, we are going to say that the change in moment is the area under the shear diagram. And that the slope of the moment diagram is equal to the shear. So let's start first with this one. I want to know what the change in moment from 0 to L is. That should be equal to what? The area under the shear diagram from 0 to L. Go up. What's the area in the shear diagram from 0 to L? Well, it's a rectangle. Area of a rectangle is base times height. Base is L, height is P, area is, and that's a positive area. So that means if I start at 0 and change positive PL, what do I get? PL. Now, again, you can probably see there's a lot of different curves that could fit that. Which one is correct? Well, the slope of the moment diagram is equal to the shear. Let's go up here. What's the value of the shear here? Right here at the beginning. What's the value of the shear here in the middle? What's the value of the shear here? What's the value at the end? What's the value anywhere? So what's the slope of the moment diagram? P. Is it positive or negative? Does it change over the length? What kind of curve has a constant positive slope? A straight line. In fact, you could define it as 1, 2, P as the slope. See? Now, rerun. What's the change in moment from L to 2L? Aaron, the shear diagram. Let's go up and see what the shear diagram has to tell us. Nothing. No change. So if I start at PL and I add nothing to it, I get PL. The shape of the curve between these 2 points is given by this. And the slope is, what's the value of the shear? 0. 0 slope is a horizontal line. Do you see a pattern? It's not going to change. It's going to be the same thing over and over. The curves will change. The problem will be distracting. But the theory, the thing I want you to focus on, will not change. Just the application will be different. Let's do it again. So from 2L to L, the change in moment over this section, given by our equation, tells us it's the area in the shear diagram. So from 2L to 3L, what's the area of this part of the curve? Minus PL. So if you start at PL and it changes minus PL, you get to 0. Excellent. I'm happy. I found my way back. I left breadcrumbs and I picked them up and came back. Here they are. So that's good. Now what's the shape of the curve in between? Well, according to this, the slope of that curve is equal to the shear. And what is the value of the shear everywhere in that section? It's constant and it's negative. So there's only one curve that will give us a constant negative slope. And if you check that, you'll get minus p to 1. And there's your moment diagram. So the question becomes now, as a structural engineer, what is the maximum moment in this beam? Where does it occur? Anywhere between L and 2L. If you look at that carefully, you might recall from the freshman class, 11-12, that's the way we loaded our reinforced concrete beams. And that's one reason why we really only cared about moment in the middle section of the beam, because the moment dropped to 0. And why we only really cared about shear in those in thirds. We never worried about shear in the middle because there wasn't any shear to worry about. See, it all connects together. It's like a big happy circle. The trick is to stay on track and just keep going round and round and round. But your radius will get bigger and your circle will get larger. So that's your job. Stay on the track, get a big radius. That's mental radius. Okay. So any questions about that? We'll do many, many more, but this is a good place to turn this off if I can get to it. Production problems.